Can everyone see this?
Yep.
Okay, we're good. Okay. Good morning, everyone. We are Tune In, Tune Out. I'm AJ Gears.
I'm Celine Lee.
I'm Kyler Mintoff.
I'm Ransford Entry.
And we're building Tune In, Tune Out, a selective noise isolation system. In the past 10 years, there's been a steady rise in the proliferation of active noise cancellation ANC headsets. They went from being fancy feature devices to the everyday device for just about everybody. The market is estimated to reach $9 billion by the year 2024, and there's been a 14% compound annual growth rate in recent years. Noise pollution is a large and regular issue, particularly in cities, public transit, and school campuses. The noises are distracting and disruptive to your mental state. What the problem is, current approaches to this issue are either all in or all out. You're either getting everything canceled and you can only hear the music you're blasting or white noise, or you're canceling nothing and you're at square one. Your current noise canceling headphones have a lack of personalization, are not interoperable, and are not particularly focus assist friendly. That's where TITO comes in. TITO lets you tune in what you want to hear and tune out what you don't.
In order for TITO to make sense of the device, we had to design the product to meet certain specifications. First, TITO needed to be fast. This is crucial because a latency or lag greater than 300 milliseconds causes a noticeable delay, making face-to-face conversation frustrating. To solve this, we use onboard digital signal processing in a Raspberry Pi. Additionally, we use Bluetooth 5.0, which is the fastest Bluetooth protocol for our data transfer needs. The device also needs to be easy to use. We created a mobile app in which the user controls the entire device. This means the user does not have to touch any knobs on the physical device. TITO also needs to provide a high-quality audio experience. This first starts with a clear microphone. And then in the digital path, we use a 48 kilohertz sampling rate, which provides enough samples for the whole frequency range, and we communicate using serial peripheral interface. Lastly, we knew that TITO needed to be portable. For this, we designed a 5-hour battery life on a rechargeable battery, and we kept the device light and be able to snap on to existing headphones.
So how do these all components work together? TITO is more than a product. It's an entire user experience, and this principle guided us in our development. Firstly, each ear has 3 microphone inputs. Each microphone is spaced out such that it can pick up a sound in a distinct and angular direction. The signals from these microphones are spread into an amplifier, where it is split into 2 separate paths, a digital path and an analog path, which we'll touch on later in the presentation. In the analog path, the signals are all added together and fed into programmable bandpass filters, which the user sends commands to via the user-facing mobile app through the Raspberry Pi, which is the central hub of TITO. In the digital path, the signals are fed into an ADC and communicates with the Raspberry Pi via Serial Peripheral Interface Protocol, or SPI. Again, the user sends commands via the mobile phone app to the Pi. All these signals are then added in the end to the final TITO experience for the headsets.
The technology breaks down generally into hardware and software breaking out further into generally digital signal processing and the app. So for the hardware, we designed 3 custom PCBs to house a 6 microphone array, as well as our control hardware and tunable frequency filter. All of this fits inside the 3D printed casing that snaps onto existing over-the-ear headsets. The signals that are picked up by the hardware are also streamed digitally to the processor, where we perform DSP. Our algorithm leverages microphone directionality, which is the same technology used in the speakerphones of the smartphone in your pocket. And we do this in order to isolate the sounds that even share the same exact frequency or the same areas of frequency.
We also have the companion app that we mentioned earlier, which users will be able to use to interact with their TITO device. We built the app from scratch using Kotlin and Java, which is important to us so that we could have as much control over the Bluetooth hardware stack as possible, instead of opting for an app builder approach. Using Kotlin was also beneficial because it enables easier cross-platform development for iOS, should we choose to do that. We designed a 2-socket streaming approach for the digital path that Ransford mentioned in our system diagram, so that we can use their headphones, users can use their headphones as they normally would, which is made possible by leveraging the Bluetooth Advanced Audio Distribution Profile, or A2DP, to perform tasks like play music, even while cancellation occurs. Then we had the cost considerations that we had to make. And at the end of our allotted development period, the total cost to build our device came to about $175, which is still significantly cheaper than the Bose headphones I'm wearing right now. We then calculated that at scale, using PCBWay's component calculator, our device would cost around $55. We see a significant cost decrease coming from replacing the Raspberry Pi with a cheaper and dedicated microprocessor or controller, which could do the same job. And then we had some ethical considerations to make because with great power comes great responsibility. We recognize that inaccuracies in frequency range isolation could pose a problem if they do occur. We accounted for this by incorporating a lookup table into our system design in the Raspberry Pi so that there's consistency in the voltage input or output that controls our tunable filters. Then removing important sounds would also be an issue. And this is something that existing noise cancellation already does. It cancels everything out. Our design is actually centered around improving on that. Our digital path also enables us to do additional signal processing to determine important sounds without slowing down the user's auditory experience. And in further iterations, important sounds will be added back through the digital path. And then lastly, privacy concerns. And this is not something that's unique to our TITO device. This is something that the industry at large deals with. For example, AirPods are able to live stream conversations in other rooms. As the industry adapts to these issues and new standards develop, so would our iterations of our device as well.
Lastly, we wanted to talk about how we ended up on this snap-on solution. During early brainstorming sessions, we had envisioned a central hub that could be placed in a room, such as a lecture hall, that all people or students could connect to have their selective noise isolation. We quickly realized that this box, for so many users, would have to have a large computing power, and additionally, it wouldn't be very portable. In the fall semester, we designed this PCB where we were going to utilize only a digital path. So we were doing digital signal processing and active noise cancellation. We quickly realized that the latency coming from all this calculation on the Raspberry Pi created a latency that was too large to be allowed. We then realized we needed to integrate a mixed signal approach. Doing this, we created an analog tunable filter where the audio would mainly be passing through, and we combined that with our knowledge from the fall semester of digital audio to create our final product, which is a combination of the analog and the digital. Thank you for tuning in. We'll now place the link in the chat.